We will start with a very small recap that what we have done last day. That we have realized that we realized that there was a issue in singular perceptron for solving some nonlinear problems. So that's why we have a solution, that is what we have seen, Cover's theorem. So in a very small, in a brief overview, the Cover's theorem is something like it says that if uh, if a particular set of points is not linearly separable in n dimensional space, then it may be linearly separable in some higher dimension which is more than n. Now, to map from a lower dimension to higher dimension, we actually found that we can utilize a vector of transformation function phi, where this phi x is a vector. Each and every element of this phi x is itself a transformation function which takes the input x as a, I mean, whole input vector of n dimension as a input, and it individually operate on those n dimensional vector. So every phi r1, phi 2, in this way phi m1 is the new dimension that we will get. So for each and every phi we'll produce some output. So as a result, in the output side we will get a n dimensional vector, right? So, and sorry, m1 dimensional vector, which is definitely greater than n, which is the input dimension of the input data. Now, how we can implement this Covers theorem? The implementation is actually through what we have seen is multi-layered perceptron, right? So why it is multi-layered? Because we have an input layer and we have an output layer, and in between input and output layer we may have more than one layers. That's why it is called multi-layer. That is the only difference between single layer and multi-layer perceptron from the architecture point of view. Okay, so now what we can do, we can move further here. That so ultimately when we are working with some data, say this is the input layer, so whatever data that we will feed to this multi-layer perceptron will be through these input layers, right? And this data that we have fed, data we will feed means basically, suppose that we have some vector x of some in dimension. So definitely the number of neuron present in this input layer has to be n, so that each and every n values should be fed to the input layer, right? Now these neurons present in the input layer will forward the data to the next layer, depends upon definitely some activation function and all. So the functionality of the neuron remains same, what was there in single layer perceptron. The difference is that we will have some more layers which will create more complex structure, and obviously the problem that we have faced in singular perceptron, that it is not able to you know solve the nonlinear problems, that can get resolved. Now naturally question comes that what we have in the output side, the number of output, in the number of neuron in the output layer will again depend upon the problem. Okay, suppose that you have a data set and the data set has, say, for each and every pattern, say there are 5 features. Each and every data point is represented by 5 features. Okay, and there is one desired result, only one. So if I want to feed this data to a multi-layer perceptron and want to get some result, So naturally from this data set, I hope it is clear that you need 5 neurons in the input layer to feed 5 features of each and every data point, and in the output layer you will have only one neuron because your desired result is only one, right? Now it is not only the case, maybe the desired result can be of more than one value. In that case, based on that, the number of neuron in the output layer will vary. So in this particular diagram, I have just generalized an architecture that maybe a multi-layer perceptron, or in short MLP, can be look something like this. Some number of neurons in input layer, some higher number of neuron in the hidden layers, and some lower or maybe one or maybe any number of neurons in the output layer, depends upon problem. So now question is that if we assume that we have say some n number of layers in the output layer, so that means definitely we are giving some inputs through this input layer that I just told you, and we are getting some output from the output neurons of this output layer, right? So, and it is very natural that we have n number of, if we have n number of neuron in the output layer, that means definitely we have n number of desired result for that particular data point, right? So that n number of desired data point is given by d1 d2 like this. Anyway, it is not m, it is considered as m. Okay, so whatever m, n, p, whatever, this is nothing but an index. I mean, it can vary. Like value of m can be 3, can be 4, can be 5, can be 2, even can be 1. Anything depends upon the problem. Anyway, so now see the data. If we concentrate only one neuron, because the strategy of a neuron of one neuron of output layer is basically similar with the other neurons as well. So to understand what exactly happening, you can concentrate only one neuron of the output layer. Okay, and others will just, it's a simply copy of the same strategy, right? So if you consider only this neuron, so we have some output here from, and we have some desired value in that from that output neuron. So definitely from the very beginning, it's not expected that whatever desired will, the same value will come from the output. So there will have some error, and that is what is represented as E. So for the first neuron it is E1, for the second one it is E2. In this way, since we have m number of neurons in the output layer, that's why total E1 to EM, like all these errors are given. Now question comes that if you can recall what we have seen in single layer perceptron, that the error equation, if you see that what we have done there, that based on this error actually we calculated the derivative of error with respect to the w. W is what? W is the weight between the input to the output layer. In case of single layer perceptron, I am saying whatever, but W means it's a weight between the output layer neuron and its previous layer, you can say, right? So that means this error E1 is generated because of this output Y1, right? And this output Y1 generated based on the value of the W connected with this particular connection and this connection and this connection, because by these three connections mainly you are connected with the previous layer neuron with this output layer neuron only, right? So that means derivative of W with respect to this error, I mean sorry, derivative of this error with respect to these W's, it's pretty easy to find out. There is no doubt, there is no problem. We can do that. The problem that we will face when we will try to evaluate derivative of this error with respect to this W, because you know whatever outcome you are getting from this output layer Y1, this is actually flown from the input layers, from this input layer neurons, it has some, some data is fed towards the next layer. From this layer, some another set of values fed to the next layer. From this layer, some another set of values fed to this output layer, and then we are getting y1 as a result. So that means you cannot say that y1 is because of only this w. It is a combination of these, all these w's of this layer and this layer, all the set of w's of intermediate hidden layers, all the w's of intermediate, I mean input and hidden layers. But the problem is that these w, all these previous layers w, is not directly connected with e. So what to do? We have to understand that, right? So what actually we will try to do, we will try to back propagate this error value in some way towards this side, in the sense, like we will get some derivative of error with respect to this w. That derivative value will be used for find the derivative of error with respect to this w. So that means, in another sense, what you can say, that this error is somehow back propagated from output towards input, like this, in opposite direction, right? And that is why the algorithm that we use to find the derivatives and continue this learning is called back propagation algorithm. So in case of multi-layer perceptron, we will basically start with back propagation algorithm.